In the lecture today, we're going to be talking about a couple topics, the first of which is the general economic environment. We're going to talk very briefly about a couple of basic concepts and then talk about generally competition in economies and the way in which we're going to model price and demand relationships. And then from there, we're going to build out cost functions, revenue functions, and talk about different scenarios where that might apply and how we can optimize or maximize revenue and profit in those situations, and also how we can figure out sort of what our break-even points are in terms of costs and revenue and so forth. So just a couple very basic concepts to get out of the way right off the bat. So first of all, consumer goods and services. What do we mean when we're talking about consumer goods or consumer services? These are things that are directly used by people to satisfy their needs or wants. So if you are a consumer and I say, what are the things you buy? You might say, well, I buy food, I buy paper, I buy housing, I buy gas, I buy insurance, you pay for your education, you use technology, you buy clothes, right? All of these things directly used by people to satisfy needs or wants. Now, these are distinguished from producer goods and services, which these are used to make consumer or other producer goods and services. So this might be things like mills or factories or equipment or trucks. Not my personal truck that I use to drive around, but trucks that are used to ship goods around the country. A couple just definitions from your book that I think are useful as we start to think about like revenue and costs and demand and so forth, that there's these two different categories of things, and they'll come up again much later in the semester as we think about things differently for them, but for now that's all you really need to know on those. Another concept is competition. So in economics, an idealized economy has perfect competition between all the different actors, or all the different sort of businesses or entities in it. And the opposite of that would be a perfect monopoly, where a single entity completely controls the basically prices. But in this idealized economy, let's look at a relationship between price of goods and their demand. Demand being, how many goods are you selling? If you sell 100 goods, the demand for those goods was 100. Okay? So the relationship between these two things, it turns out in this idealized economy, is a line that looks like this. The more demand there is for a good, the more competition there will be for selling that good, and the lower the prices will get. The less demand there is for good, the less competition will be, and the higher price can be, the higher the price of the good. And as we look at data in the real economy, a lot of things look like this. Initially, when cell phones were not very common, early in their adoption, you can think of computers the same way. They were extremely expensive, but as they became ubiquitous, the prices just came down until now you can get a cheap cell phone for $30-$50, or a computer for maybe $200, whereas the initial computers might have been $20,000. So the equation for this, P, the Y, in this graph is equal to A minus BD. is a generalized equation for the relationship between price and demand, or demand can be said to be A minus P over B. So these constants A and B are going to differ for different situations, but this can relate what price will we have for the good, how is that related to the demand for it. Okay, so now we'll look at down here, we're going to be looking at how is revenue related to demand. So let's look at another graph here. We're going to say this is total revenue and this is demand. And total revenue is this term that means how much money are we bringing in, okay? So if I sell 100 glasses of lemonade for 50 cents each, 100 times 50 cents is $50. That's my revenue that I brought in. So I'm multiplying the price that I'm charging times the demand, how many I sold, okay? This isn't the profit. I haven't talked anything about costs yet. All this is the revenue. Okay, but up above we defined the price is equal to A minus BD in this environment. So TR, I'm going to replace P with A minus BD. We'll multiply that by D. And so we multiply this out and we get AD minus BD squared. So the total revenue as related to demand is AD minus BD squared, and it turns out this looks like this. Okay? As the demand is low, when I multiply the demand times the price, which the price is going down as demand goes up, as we saw above, the total revenue increases as demand increases, but at some point the price gets so low that it starts dropping off. And so we have at the top here some max revenue. And if we want to figure out what is that maximum revenue possible, all we have to do is take the derivative of our total revenue function, set it equal to 0, and solve for the demand that makes that so. So we'd say it's dTR dd is equal to, and now we're taking the derivative of this function here, and we get with respect to d, and so we get a minus 2bd, and we're going to set that equal to 0. And we can solve for the d that makes this so. We're going to call it d hat, a minus 2b. I mean a over 2b. This is the demand that maximizes total revenue. And what is that maximum total revenue? All I need to do is plug in my value of t hat into the original equation. I'm not going to show all the math for this, but TR max equals, we get a squared over 2b minus a squared over 4b, which equals a squared over 4b. Okay, so we've got this and we've got this as two major outcomes. Okay, so what we've established is, what does this price and demand relationship look like? What is the total revenue function? And then how do we figure out what is the demand that maximizes total revenue, and what is that maximum total revenue? All right, next page. So total revenue function, we just did this on the previous page. So just as a reminder, TR equals PD equals A minus BD times the demand, which is AD minus BD squared. And maximizing revenue, we're going to call it D hat, and it's A over 2B, and TR max is A squared over 4B. All right, and you'll notice I've scratched off here where it says cost volume break-even point relationships. I'm just going to talk now about the cost function. So I've talked about the revenue function. Now what's the cost function? So the total costs that I'm going to incur, this relates to the definition, the cost definitions we are learning. Total cost is equal to two things, what we call the fixed costs plus the variable costs. Variable costs are those that vary with demand, and we're going to say that C sub V is equal to little CV times demand. So if it costs me $20 to make a chair and I'm going to sell 100 chairs, my variable costs for that is going to be the $20 per chair times 100 chairs, and I get my $2,000 of variable cost for the chair. But I also have a fixed cost associated with making chairs, all my factory and keeping the lights on and all that kind of stuff. So that's my fixed cost. So the total cost function, C sub T, is going to be C sub F, fixed cost, plus, I'm replacing big CV with little CV times D. All right, so that's basically it. I've now got a revenue function, which is up here at the top of the page, and a cost function, which is down here at the bottom. And I also know how to optimize or maximize revenue. But companies don't usually care about maximizing revenue. They're not in the business of trying to maximize revenue. They're trying to maximize profit. Profit is going to be the difference between what you bring in, the total revenue, and what is going out the door, the total cost. So next page, we're going to start looking at that. Okay, so we've got two scenarios. The first scenario is, as it says here, scenario 1, where the price is dependent on demand. That's what we've been talking about. We've got that decreasing function that relates price and demand. That's scenario 1. Scenario 2, toward the bottom of the page, is going to be a scenario where the price of something is not dependent on the demand. In other words, it doesn't matter how many things people are buying of it, the price is independent of that. We'll talk about that in a minute. But here we're still in the world where P equals A minus BD. And again, my total cost function is C sub F plus CV, or CF plus little CVD. And my total revenue function is PD, which is A minus BD times D, which is AD minus BD squared. So on the graph on the left, you can see there's my total revenue function, the parabola, AD minus BD squared. You can also see the total cost plotted, right? There's a linear relationship where the fixed cost is the y-intercept, and then the variable cost per unit is the slope, that going up. And we're defining now the profit is going to be the total revenue minus the total cost is the profit. So you can see on this graph, the profit is that difference between what's coming in and what's going out. It's that shaded area, all right? So mathematically, we have the total revenue, which we're going to call AD minus BD squared, minus the total cost, CF plus CVD. That's the profit. I'm just going to rearrange these, do some algebra. I get minus BD squared plus A minus CV times D minus C sub F. And you'll see in a minute why I'm rearranging it in exactly this way. So this is my profit function now. My total profit is revenue minus costs, and we've got a profit function related to demand. As I said, we're usually in the business of trying to maximize or optimize our profit. So in order to figure out what is the demand that would maximize this profit, I'm going to take the derivative of it and set it equal to 0 again. So D profit dd is equal to, and the derivative of this thing with respect to d winds up being a minus cv minus 2bd, and we're going to set that equal to 0. And you can convince yourself that that's so. So now we can solve for d. We're going to call this one d star. D star is going to be equal to a minus cv over 2b. So before we had d hat, that was the demand that optimized revenue. And now I've got d star, so this is the demand that optimizes profit. So looking at this figure in the upper left, you can see this is where this difference between the revenue and the cost is going to be greatest. And you can see there it is, d star. So keeping d hat and d star separate, d star is better, right? It's got a star, it maximizes profit. D hat, it's cool, it's got a hat. That's a neat thing, optimizes revenue, but it's not as good as being a star. Okay. All right, so let's look at the break-even points now. Break-even would be where my revenue equals my costs. So looking on the figure, we've got over here, this point right here is a break-even point. And it's defined here as d prime 1. And then over here on the right-hand side, we've got another break-even point, and this is d prime 2. If I want to make a profit, my demand needs to be between those 2 points. Okay, so let's figure out what those are. At the break-even points, the revenue is going to equal the costs. Okay, so my revenue function, AD minus BD squared equals my cost function, CF plus C sub V D. Okay. Rearranging this like I did before, minus BD squared plus A minus CV D minus C sub F equals 0. I put them on the same side, done some factoring and so forth, and I get this. Now when I want to solve for what is the value of D that sets this equal to 0, I can see that this is a quadratic equation. And it's in a form now that makes it easy to use the quadratic formula. So, what are the values of D that make this true? We're going to call them D prime, and we're going to write the quadratic formula here. It's minus B. Now my B in this case is this term, right? That's going to be my B. This is my A, and this is my C. So when I do B squared, it's or negative b squared, I should say, I'm saying squared. Negative b, that's what the first term in the quadratic formula is, minus a minus cv, plus or minus square root of b squared, a minus cv squared, minus 4ac, minus 4a, which is negative b, c, which is negative c sub f, all over 2a, which is 2 negative b. If I plug in the values of these into here, I'm going to solve for the two values of d prime, one when I use the plus and one when I use the minus, and I'll get d prime 1 and d prime 2 as my break-even points. We'll do an example problem with that in a minute. In scenario 2 is a scenario where that price-demand relationship we talked about earlier doesn't apply. The price is independent of demand. Okay? In this case, here's what our functions look like. Our total revenue function is just price times demand, and we can't further simplify that. And our cost function is still C sub f plus CVD. So when we plot these, as we do on the left, you can see our total revenue is just a line going up, our total cost is just a line going up. And so here, if we want to maximize the profit, where is this maximized? It's maximized at the maximum feasible demand, right? Ideally, we just keep going to the right until our profit grows infinitely, but there's a maximum feasible demand. That's where we want to be. Where's the break-even point? Here it is. It's called D prime. At the break-even point, total revenue equals total costs, or PD equals C sub F plus CVD. Right, setting my revenue and cost functions equal to one another, and I solve for D prime equals C sub F over P minus CV. Okay? So that's how we maximize profit. Let's do an example problem where we bring this together. In this example problem, I've got a product that I'm selling whose fixed costs are $73,000, whose variable cost per unit is $83 per unit. The price and demand relationship, P equals 180 minus 0.02 times demand. Remember, this is in the form P equals A minus BD. And we want to know what is optimal volume demand. How many of these do we want to sell? And once we do figure that out, we want to confirm profit occurs. All right. So we've already figured out for the case where this applies, this price-demand relationship, that's scenario 1, we calculated already that D star is equal to A minus CV over 2B. So what's A? Well, A is this 180 from the price-demand relationship. Our CV is 83. And we divided by 2 times B. B is this 0.02. And we calculate that D star is 2425. If we sell 2,425 of these things, we are going to maximize our profit. Let's confirm that a profit occurs. Total revenue minus total cost. We want this to be positive. So we get our total revenue is P times D, but we're at D star. So D star times P. Subtract off our total costs, our fixed cost plus CVD. And so D star was 24.25. The price is A minus BD, so it's 180 minus 0.02 times 24.25. Subtract off my costs, which is 73,000 plus $83 per unit times the 24.25, and we get $44,612. So a profit does occur because that's positive. Now in part B, we want to figure out what are the break-even volumes. So these are the D primes. And again, we look back to the previous page and we saw our quadratic formula. D prime is equal to negative A minus CV plus or minus the square root of A minus CV squared minus 4 negative b negative cf all over 2 times negative b. So let's plug these in. We've got negative, our value of a is 180, minus CV, which was 83, plus or minus square root of 180 minus 83 squared minus 4 negative b. B is 0.02, so it's negative 0.02. And CF is 73,000, so we've got negative 73,000 all over 2 times negative b, negative 0.02. So I do a lot of arithmetic, and I get that my break-even points are 932 and 3,918 units. Okay, so that concludes our lecture on the revenue function, the cost function, the price and demand relationship, and then optimizing both revenue and profit and optimizing profit in both scenarios, the scenario where price is related to demand and the scenario where it's not.